Hey, good afternoon, ladies and gentlemen. Welcome to the 10th annual Donald M. Mattox tutorial. Our speaker today is Professor Allan Matthews, who is Professor of Surface Engineering and Tribology at the University of Manchester. Allan has been active in SVC for many years. He's been on the board, he's taught classes, and last year he got the Mentors Award. In his new position in Manchester University, he used to be at Sheffield, he is providing leadership in coding and technology research for the newly created Sir Henry Royce Institutes for Advanced Materials Research at Manchester University. This is a $350 million effort by the UK government to set up a world-class tribology materials research group. Allan is also the editor-in-chief of Surface and Coating Technology magazine, which most of you are familiar with. Obviously, the title of his talk is New Challenges for Industrial Tribological Coatings. So with that, I'd like to introduce Professor Allan Matthews.
Okay. Thanks. And I guess I press the button off, do I? First of all, can I say what a pleasure it is to be giving the Donald M. Mattox tutorial presentation. I've known Don for many years. He's been involved in this for the best part of 30 years. And we all owe a great debt of gratitude to Don and to Vivian for keeping this show on the road for all those years. I doubt if it would be happening if it wasn't for the hard work that they'd put in over these many years. So we really do owe them a huge debt of gratitude. And certainly from my point of view, Don's had a big influence on my career. So thanks a lot, Don. Okay, so Don said talk about something practical, or was it Vivian that says talk about something practical? So it's called New Challenges for Industrial Tribological Coatings. It could even be called New Challenges for Industrial Tribological Coating Providers, because these challenges apply whether you're an end user or whether you're a producer of coatings. So because I wanted to make it practical, I've been to many industrial contacts and asked them what they think. And therefore, a lot of this talk is going to include input from industrialists, in particular from Lucy Berg at Caterpillar, from Steve Franklin at Philips Electronics. There's some content from Keith Legg and also some input from Dave Rickaby at Rolls-Royce. I'm going to start by talking about drivers for change in coating process usage, and that includes legislative and regulatory impacts. I just realized that I didn't press on with the right button, so do you want me to go back, or we're okay with that one? And then talk about some design manufacture aspects and selecting and testing coatings for industrial applications. And then, if there's time, a recent UK perspective on challenges facing the coating sector. So, surface coating developments are being driven by technological breakthroughs and also by increased demands being placed on coatings. The increased demands may be based on legislation and regulation, such as environmental and health and safety, or by performance requirements such as needs to reduce friction and wear. So we've got technological pushes bringing along new developments. As we know, there are many new developments coming along in PVD, plasma-assisted PVD, but also by that pull from the regulation, the legislation, and by the performance pull. And one of the regulatory demands that's come along, which has been referred to a few times at this conference, is the so-called REACH legislation. What is REACH? It's an acronym, stands for Regulation for Registration, Evaluation, Authorization, and Restriction of Chemicals. It actually entered into force in the European Union in 2007, and contains a number of deadlines which will be progressively implemented until June 2018. And this becomes European law in all the member states. And it places a greater responsibility on industry to manage the risks that chemicals may pose to the health and to the environment. And it's intended to ensure that substances of high concern are eventually replaced by less dangerous substances or technologies where suitable economically and technically viable alternatives are available. So it replaces about 40 other pieces of legislation. So originally, legislation in this area only covered new chemicals. But now this legislation covers all chemicals. So there were like 100,000 chemicals which weren't considered for this legislation, but now they're all in there. And in fact, there are something like 30,000 chemicals which are of immediately concern based on the tonnage quantities of usage, because REACH only covers certain weights and volumes of usage. And it's a big deal if you're in Europe. And the idea is to try to replace the thing on the left with the thing on the right. Of course, we'd like to see the thing on the right to be more vacuum deposition as well as cleaner electroplating, as we heard from the guy from VTI this morning talking about the use of chrome as an alternative to electroplated chrome, PVD chrome. So concern over this, so you guys in the States might think, well, what's it got to do with us? You know, this is in Europe. But in fact, as we heard from Keith Legg a couple of years ago at this event, there are many people in the States concerned about this legislation. And there are several US organizations that are concerned about it. Some of them are listed here: SERDP, ASTCP, Assets Defense, NASF, ACE, Emerging Contaminants Initiative from the Office of OSD and ATL. So these are USA organizations, but they're still concerned about it because they can see that this legislation is likely to affect producers around the globe, in fact. If you're selling stuff into Europe, or you can probably imagine that this legislation will start to impinge on all countries eventually. So one of the main important people in the States are the Assets Defense, and they are particularly interested in replacing these chemicals in the defense sector. So they're looking for alternatives to hard chrome, to cadmium plate, to high VOC paints, chromates, etc. And they also offer an online information source for DoD organizations and contractors. So again, we saw from Keith the way this is having an effect already on the F-35, implementing new non-chromate primers, testing aluminum plate to replace nickel cadmium on electrical connectors, new bushing materials, new aqueous electroplates, nanocrystalline cobalt phosphorus to replace hard chrome, implementing high HVOF, tungsten carbide cobalt chrome as an alternative to hard chrome, and other changes coming along already. Other ones going to be introduced: cold spray aluminium for magnesium gearboxes, chromate-free fuel tank coatings, chrome-free sealants, nanocomposite cobalt phosphorus for internal diameter coatings, for hydraulics. All these things are being looked at. And also on helicopter systems, people are looking at zinc nickel as a replacement for cadmium, various plasma electrolytic processes for magnesium gearboxes, and all these other things. So you can see that this is a real driver. It's affecting things already. These legislative and environmental changes are driving the use and selection of coatings and development of new ones. And this has to be carried out within the constraints imposed by the regulatory pressures, such as those environmental and health and safety concerns. But it's also driven by performance demands. For example, energy concerns, sustainability, and efficiency demands that are coming along. The big problem, as I see it, if you are an end user of coatings and you want to choose what coating you should use as an alternative, there are a lot of application requirements that you have, and there are a lot of possible solutions, a lot of coatings out there which you could maybe use. And it's a major challenge how people select, test, and validate new coatings. And if you like, that's the first demand for tribological coatings that I see. We've tried to develop a structured way to make that selection, and we've talked about listing what's needed, and then what is possible, and then trying to progressively eliminate coatings based for good reason. The wrong thing to do is to choose a coating, see if it works, and if it works, use it. That is not the best way to do it. The best way is to assume all coatings work and then eliminate them for good reason, and then you don't eliminate better solutions by default, because there's always a danger if you just use a coating and it happens to work, you assume that that's the best, but it isn't necessarily. So you've got to go through this procedure, and it's very, very challenging. If you think about the numbers of requirements for an application, and you think about all of the properties that can be influenced by a coating, you can imagine that it's extremely complex to make all these interlinks and interactions to try to choose what coating would meet the application needs. Well, you can get some way to this by eliminating the ones that don't fulfill the basic process requirements in terms of achieving tolerances, geometries, masked areas, all that kind of stuff. So you can make an initial elimination, but you've still got to find the coating that fulfills the performance needs. So the things that influence the tribological response are very much related to deformation and the deformation of the system. What's the load on the system? What are the stresses on the material? What's the resultant elastic and plastic deformation? What's the fracture situation? And therefore, what's the wear mode? So you've got to go through this, but you've got to do it for the different kinds of tribological types. And what people used to do is they just used to look at the wear mechanism, and they used to say, well, this application is abrasion, and we'll choose the coating to eliminate that abrasion. But I feel the thing to do is to look at the contact type, because the different wear mechanisms can occur in all the contact types. So what I mean by that is this, that there are several types of contacts. You could have sliding, you could have impact, you could have abrasion, and you could have fatigue-type mechanisms like fretting or just straight surface contact fatigue. And what I've done here is I've tried to identify the requirements of these different contact types. And the first thing to note is it isn't just hardness. You know, some people will believe that all you need is a harder and harder surface and that eliminates wear. That just ain't true by a long stretch of the imagination. In fact, one thing that we often emphasize is the ratio between the hardness and the elastic modulus. If you follow the stuff we write, we often talk about it because it defines something called the elastic strain to yield. So if you have a high ratio of hardness to modulus, it means you can stretch the coating a lot before it yields. And that's more important than hardness, believe me. Another thing we talk about is the load support. So it's the support that the underlying substrate gives to the coating. And again, people talk about load support, but they don't define what they mean. I mean, we all realize load support's important, but what do we really mean? Well, a lack of load support can make things fail in different ways. You could, if you don't have adequate load support on under the coating could fracture, the coating could debond, the coating could, the substrate could elastically deform, that could take the component out of tolerance. The substrate could plastically deform, so it could take it out of tolerance permanently. And the substrate could fracture, or you could get plowing friction due to the increase in deformation. So load support's important. So that's one thing that I believe is important as you develop new coatings, is to consider the underlying substrate and the coating as a system, not just a coating. You'd be surprised how many papers we get to my journal. I've done a hard coating on titanium to improve its wear resistance. No, you haven't. And then they do a test at a few grams to prove that this coating can survive. But then no way would it work on a real tribological load. So you do need to have the load support. So one way to represent this is that we have a diffusion treatment, say, to improve the load support. Maybe a thin film to give either improved tribology in wear resistance, or a soft lubricant film, together with a suitable substrate to combine them together. And that's what we mean by a duplex treatment. So we think there's a big move towards duplex coatings and diffusion treatments. So I'm going to consider an example from Lucy Berg at CAT, who gave a great presentation here fairly recently, and I thought it gave a perfect representation of what's important to an end user when they've got to select a coating. And in her talk, she said, first of all, you've got to identify the function of the component and the contact, look at the wear contact type and the wear mode, and then make your selection. So she said, understand the component and its intended usage, fully understand contact types and wear modes, and select the solution. And the example that she gave was a inlet control valve on a common rail diesel fuel pump. And she decided this has 4 functions. One is to maintain a seal for angle geometries in impact and in sliding. It has to resist cyclic impact loading. It's got to resist high velocity fluids and gases. And it's got to accommodate debris. And that means that the surface should elastically deform locally to accommodate the debris, and then the debris can be washed away, or the debris can be crushed, so you need a hard coating to crush the debris and then wash it away. So there are other requirements to consider when you make the selection. The temperature requirement, the hot hardness has to match the operating temperature for the impact resistance. There's got to be thermal stability at the operating temperature for dimensional stability, and the tempering temperature has got to be higher than the coating deposition temperature. You've got to be able to manufacture it. You've got to have an acceptable tool life in manufacture. You've got to produce something that's devoid of burrs if you're going to coat it. And you've got to be able to handle it. Appearance has got to be right, and you've got to be able to transport it. And then there may be geometrical features which you've got to maintain, like maybe a threaded region that shouldn't be coated, shouldn't be made brittle, or maybe you've got to avoid edge embrittlement. So there are all those features. So that's defining the function and the requirements. So that's what they do. And they do it using those contact types that I mentioned. So they will look at the function and the contact types, and they will categorize them according to those that I gave you. Well, that's the first step in identifying the testing that they've got to do on these coatings in order to validate them for their application. So you're trying to eliminate unwanted wear, because unwanted wear leads to valve leakage. You've got to maintain the seal, you've got to resist the fluid flow, you've got to accommodate debris, and you've got to resist cyclic impact loading. That's what I said in different geometries. So you understand the wear mode, then you've got to confirm the wear mode with field trials. So what they then do is they do the tests, and they make sure that the behavior they see from the coating is simulated in the actual between the field trial and the in laboratory test. So they'll do lots of microscopy just to check if the failure of the coating is as they see in the field. So an awful lot of that kind of microscopy to understand how it operates and what kind of deformation and bedding in they get. And they also then confirm what are the primary contact and wear types. So in this case, they really did identify that impact wear was important in their application. So they did a lot of impact testing, and they got the solution that they were going for. So they've got their unwanted wear modes, repeated impact, single impact, erosion, adhesive wear, and cavitation. That's great. We've identified the wear mechanisms. We've seen some coatings that work. However, they also want wear. You didn't think that. Well, you wouldn't think that, but they do, because this coating has got to bed in to create the seal. So it's extremely challenging and demanding. So the valves should be designed to wear. They're critical to the performance. New parts need to make a seal before making a seal. They need break-in wear under any geometry. And the engineers need to design for a steel on steel, a steel on coating, and a coating on coating. So you can begin to see this is extremely challenging. So they look at the deformation of the asperities, on steel, on steel, and on coating on coating. And coating on coating didn't work. Coating on coating gives them a maintenance of a surface which actually doesn't wear and actually leads to failure of the coating because the local pressures are too high. So it's never simple. And what I'm trying to get across to you here is that it's not a simple case of I'm going to develop my super hard coating, I'm going to do a pin on disc, and that therefore I'm going to give it to the world. No way. You've got to be aware of industry's requirements, which are complex and may not be what you think they are, and you've got to work with that industry in their testing in order to get the solution that you need, or that they need and you need. So this is just going, again, through what they've got to do in understanding it and the different angles, different geometries, the fact that they've got to seal valves, they can't machine the fitting, the coating. It would cost far too much to finish machine to the accuracy that they need to get the seal. You've got to rely on the coating to do it. So if you coat one surface, you got valve leakage. If you coat both surfaces, they got valve leakage. You see. So they had to find a solution. Now, I'm not going to give away Caterpillar's trade secrets. I'm going to tell you what the actual solution was, and I'd get into trouble if I did. But you can understand, hopefully, the complexity that they have, and CAT is just one company that's trying to do this. We could have done this for people who are designing all kinds of other applications, where the complexity of their demands are often much greater than we, as coaters, understand. They do need to pre-coat a pre-coated surface finish, but the finer and finer that surface finish, the higher and higher the cost. And a lot of these parts are automotive parts. They've got to be done at low cost. So it is a matter of selecting the coating to give the performance in service without incurring too high a manufacturing cost. And they need to do this before, as Lucy called it, before the design goes to iron. It's not an expression I'd heard of, but I guess this is an Americanism. Before you actually decide to make the thing, you've got to get the solution. Okay, so I can tell you that the solution did involve the carburizing and the tempering and then a coating, but can't tell you what the coating is. And what's important here is coatings, successful coatings, successful surface engineered solutions are not afterthoughts. They've got to be, they're not band-aids. They've got to be designed in when you actually develop the product. They've got to be an integral part of the design process and the test procedure. And one thing about all this is that unrepresentative accelerated tests are no good in the real world. Again, I was in the meeting this morning, in the breakfast meeting about medical coatings, and somebody said, can we do accelerated tests? And I think that in that field, probably more than anywhere, you can't do accelerated tests. Now, I have a slide which I show, is in some way amusing, but hopefully it'll explain to you what I mean. Okay. So one guy, I was at a conference, and he said, you academics, you think you can do accelerated tests, but you don't get what you should get. So he said, if you do an accelerated test on an egg, you're going to get a boiled egg. What you should get is a chick, okay? And that really shows what you've got to do. You know, you're not going to get the real world outcome if you try to accelerate or if you use a test which isn't related to the real world. So we've got to address real-world challenges and give you an example of one we've worked on. We've tried to. I told you about people think they can put a thin layer of titanium and get a good wear performance. You can't. There was a guy called Tom Bell in the UK who had it in an ambition to be able to develop titanium for situations where steel's used now, and gears and bearings. And he didn't actually achieve it, but recently it has been achieved. And we've managed to develop a titanium-on-titanium bearing for a huge bearing on an Airbus undercarriage, replacing a heavy steel-on-bronze bearing and removing hundreds of kilograms out of this. And this is titanium, which is pretty incredible. I actually don't believe it, but they reckon it saves $10 million over the life of one plane, or 36,000 tons of CO2. I still don't believe that, but anyway, put it this way, it's very beneficial to them to be able to replace steel, bronze bearings with titanium. And the only way to do it is that duplex approach, where you harden the titanium alloy and then you put a coating on it. So that's a real world one. Just a word about statistics. It's important to have appropriate tests. This is a few years ago now, but we did some tests on a punch used in nut manufacture, and we tried to understand the performance of the producer. They had lots of data, and they got a lot of variability in the performance, and they didn't understand why. And what we eventually realized is that the coatings only worked with an appropriate pre-grind and polish prior to coating. And when they did this, and they had masses of data, they didn't understand where all the data was coming from, but when you homed in on it, it was the fact that they did a pre-polish and various other geometrical polishes before coating. And when they did that, they got, so this was part of a European collaborative project. The UK user had a lack of lifetime records, or had a lack of understanding on them, and was getting unpredictable results. And what I'm going to say really just applies for this application, but still the message that you've got to take a statistical approach to your coating performance still stands. And say, for example, you could get this performance, which has a higher expected life than this performance. So this one, the most likely life is 55,600 components. The most likely life of this one is 54,300. And you might say, well, my solution's better. I've got a higher expected life. But no, because this thing starts failing immediately. And that's no use to a user. No use at all. If you run the night shift at Ford and you're going to put a tool in at the beginning of the night shift and then leave it, you might come in the morning and just get a load of scrap. You are much happier to use this one, which gives a slightly lower expected life, but has what they call is a life of intrinsic reliability. In other words, there won't be any failures up down here. And you wouldn't, even though this could do 34,000, whatever it is, anyway, a much higher number, you would just use this up to that life and then remove it, because you need that confidence in the performance. So that's the other thing the end user needs, is confidence in the performance of the coating. Well, I won't go through them all yet. One good thing, by the way, that this is being recorded, so you can come and listen to this anytime you want online on the SVC site. So I am going to go a bit quicker as we go through, because I've got quite a bit to get through. So all this is going to be up there for you to see. So there's a lot of variability in mechanical and tribological test data, even under identical test conditions. You need to simulate real conditions, and you need to be aware of the statistics. And don't forget, sometimes you need desired wear, which people often aren't aware of. Now, I did also have a lot of information from Steve Franklin at Philips Electronics, and I'm actually not going to dwell on it because it is going to be there on the SVC website, but the messages are very, very similar to the messages from Lucy Berg's application. Steve's a tribologist, and he also has the same thinking. You know, he says you should set your tribological testing phenomena, understand things like the transfer layers, investigate the effects of test parameter variations, etc. It's just as rigorous as Lucy's. And he gave me a case study where they looked at progressive levels of testing from a simple sample test going up to a field trial. And he says that the only way to get representative data is to do a full field trial, but they will still start off by a simple bench test, then maybe a simulation test, and a miniature test, and a component test, etc. That's what Philips do, and he gave an example of that after making sure the goal's clear. This was one where they were testing, obviously, a coating for an iron, but they start off by doing the lab test, then a rig test, and then the real test. So in industry, this is what they do. They do very, very rigorous, because if they get this part out into the world and then they start getting claims back for failures, and it can be astronomically expensive, as we know from certain recent automotive failures. And again, this is all on the notes. You're going to see it. It's the same kind of message. State the goals clearly, ambiguously, etc. Develop the test, type of motion, the contact type, etc. So he does it. So a case study he gave me was redesign of an aerostatic thrust bearing for a wafer stepper in a semiconductor manufacturing line. So he, within Philips, he also has to help them design for tribological applications. And in the example that he gave me, this was an aerostatic thrust bearing where they were getting wear damage associated with one of the holes where the air jet comes through to support this thing. And they needed a new installation, a new equipment solution, and an install-based solution. So they had to find a solution to what they had by modifying it, and what they would do if they had a new design. And the wear was interesting. They were getting these small particles in coming through near to the orifice, and then they had to solve for those, and they needed a non-magnetic, so there's information there of the test pad that they built to simulate this wear. And I said they got these small particles between these plates, and they were becoming magnetic because of the nature of the application. So then they had to do testing where they incorporated those little particles, and they tried different alternative solutions, both for the normal sliding and for the crushing effect of this thing. So you can see. So this is for the new equipment solution, and then they had the installed base solution. So that's all going to be there online, and you can look what they did. But again, the message is the same. You've got to simulate the real world, and you've got to look at all the possible solutions and eliminate them. So Philips, like Caterpillar, and all other successful manufacturing companies, recognize the vital importance of working with tribology, coating and treatment providers at the design stage in order to optimize their products. So this is the challenge. Okay, you get the message. You've got to work with the design people, you've got to work in their validation and testing, and work for the best solution. So I said I'd just talk about a UK initiative, if there was time, and I think this probably is just time. Go ahead. So in the UK, recently, there was a study of the UK surface engineering and advanced coatings industry that's called SEAC, S-E-A-C. And it was carried out by an organization called the KTN. And the KTN is the Knowledge Transfer Network in the UK. And their aim is to capture value for the UK from science and creativity. They connect people who accelerate innovation. they address societal challenges, they enable collaboration, they help to develop and build the UK's innovation capacity, they capture value for the UK from science and creativity, and they facilitate sustainable economic growth through innovation. And have you noticed other politicians have all now started to understand innovation? The innovation ecosystem was a term that came out of the US, and it's understanding that you innovate, you create products, you create profit, it goes around, you can reinvest the profit, and you keep the whole thing going. I think it's Judith Harrison is the lady, maybe at NSF. Anyway, you can just put in, do a Google on the innovation ecosystem. It's a fantastic concept because it means that people, even politicians, understand what we do. Okay. And so these guys operate in all kinds of sectors, not only materials. And in the materials one, there are about 9,000 individual members from about 5,000 organizations, mixed of industry, academia, design, community, government, etc. And they try to link together academia, government, industry, government, etc. And in the materials sector, they look at various materials technologies, various applications technologies. And the kind of things they do is they network, they have innovation needs and dissemination, brokerage, and communications. And a big thing they do is called special interest groups. So they identify an important area for development, for technology, and they will set up a special interest group to look at that sector. So they did one in the coating area, surface engineering and advanced coatings, and had a working group. There was only one academic on it. Won't tell you who it was, but you see. Mostly industrialists, and there is some great work looking at this sector, the coating sector. And they held advisory group meetings, one-to-ones, consultations, etc. They looked at the market, the drivers in that market, the actions, barriers to innovation, supply chain characteristics. They had strategic workshops which they then analysed. And surface engineering and coating is identified as a key technology area in the HVM, high-value manufacturing sector. And they looked at previous reviews on this sector in terms of the value of the sector, and they confirmed that companies with a total turnover of £383 billion, so that's about $500 billion or more, used coatings extensively on their products, and that £140 billion worth of their products critically depended on coatings. And the coating value was about 11 billion. So you could say that 11 billion pounds worth of coatings critically affects industry with a turnover of 383 billion. So it's important. The area that we work in is critically important to most products out there. And they looked at the use in different sectors, and these numbers will be just scaled up, and the sectors will be the same for every country, but I think that they're still valid, the findings, even though it was a UK study. And it looked at it through the complete value chain from R&D through to the product, production, and even through to disposal. And they realized the drivers were enhanced product performance, cost-effective products through more efficient materials utilization, changes in business environments such as reach are affecting things, and this demand that's there now for sustainability. And I think sustainability is one of the biggest drivers for us now, for all of us. And the fact that coatings can help so much in sustainability. And supply companies need SEAC technologies applicable in different applications which are readily transferable between sectors. And you're well aware of some of the types of uses for coatings. So they wanted to, as I said, they wanted to see how they could maximize the value of innovation, how could they affect the supply chain, how could it make it part of the high-value manufacturing sector, How do we change the game in manufacturing in the SEAC supply chain and maintain competitiveness through the product life cycle? Now, we were fortunate in having a guy from Rolls-Royce, Dave Rickaby, chairing this group. And he said that he thought there was the problem they had, this is Rolls-Royce, uncertainty about the long-term performance of new coatings. High financial risk in introducing new technology. If it fails, it's disaster. Complex and costly qualification processes for certain markets, often a lack of industry standards. And they need a standard. Rolls-Royce can't put a coating on an engine unless it has a standard. Unless there's a standard they can put on a drawing, they can't use it. So it's important that there are these standards. And there was a perception that the supply chain was inward-looking and conservative rather than proactive to industry needs. Does that describe the coating sector? Might do. Somebody's nodding. So Dave showed us some fairly complicated Rolls-Royce charts and diagrams, which normally they're just for internal use, but he allowed them to be used in this study. They're in this report. And his view was that at the moment, everybody's looking at the application and solving the solution as it arises on the product. And what it should do is focus in on developing a design for manufacture capability within the coating supply chain. And that way, everybody benefits, the end user and the coating producer. And also, like I said, he demands the standards should be introduced as it's coming through that funnel, whatever it is. So Rolls-Royce see a significant need to identify, develop, validate, and standardize coating technologies with the use of robust testing to validate the coating system as fit for function at the design and product development stage. They achieve this by integrating the research base and the supplier base and working together, and they do that extremely effectively around the world, not only in the UK. So again, another one of Dave's complicated diagrams. But basically, it's all about creating project teams at the early stage, integrating the science base, the material supply chain community, and the manufacturing sector, bringing things through that developmental funnel, or whatever it is, and introducing standards. And it gets even more complicated. As I said, these will be there for you to look at and to take in. But you can see the complexity that a company like Rolls-Royce goes to in order to ensure that the coatings that are coming through are properly tested and validated. So the conclusion is that the tribological coating researchers and coating companies should get together with the product design and manufacture companies at the beginning of the product development cycle to ensure that their coatings really meet the needs of the end users. Developing coatings and processes in isolation may be interesting scientifically, but it's unlikely to provide the optimum properties in the coating and is therefore less likely to create a market for that coating. So it's in everybody's interest, it's in our interest to work with the producers to make sure they get the coatings that they need. And that report, because this is going to go online, that report is going to be, the link to that report is going to be available. These are just some bits which I didn't get through. So the link to that report is going to be there for you to get. Thanks.